Hello, hello. We're going to pick up where we left off with the Meterstick activity, and you guys, each group should hopefully have 6 to 7 data points. There's a reason why I wanted that many. You'll see in a bit why that is. But let's just review some of the other stuff just to jog our memory about vocabulary, how we speak about things in physics, and so on. So we're focusing on the point particle model, where we treat every single object as a point in space that has an assigned mass just to that singular point, even though we know in reality that the object is a lot more complicated than that, right? So we're going to say that the center of mass of each object is its location, right? So I have a center of mass, the meter stick has a center of mass. That is where the location, quote unquote, is. We learned how to find that center of mass through the balancing point, right? That was when we brought our hands together under the meter stick. It's just the point at which the object is going to balance on your finger, essentially. And we also learned what center of mass was mathematically, which I think is over here. Yeah, so we found this formula, or I just told you guys that was the formula. A lot of people were confused by the Riemann sums. Just remember, not Riemann sums, but sigma notation. All that means is sum. You're just adding up a bunch of stuff that looks like this. Just keep it that simple, guys. Right? Adding up a bunch of stuff, sum of things like this. That's really all you need to know. The I is just a placeholder for some kind of subscript for each object. So I think by now most of you guys have kind of understood that notation a bit better. We talked about systems. Systems are just when you put a bunch of objects together and you're trying to take all of them into account, right? Because at the end of the day, every single object we look at, whether it's a bowling ball or a person or a pair of sunglasses, is made up of millions, if not billions, maybe even trillions of molecules and atoms and so on. So, I mean, in reality, everything is a system. It's just a matter of what you want to focus on. There's a lot of moving parts to every single thing, even if it looks like one singular thing. So that's the fun thing about physics. We get to choose what we want to focus on. We came up with an experimental way to maybe try to predict the mass of the meter stick, right? So we identified our independent variable. I kind of revealed that later on after having you guys try some stuff out. That is where we're putting the weight on the meter stick. That was its position, right? Which would be where the center of mass is for that weight. And then we had the dependent variable. That was how the center of mass of the system changed according to where we put the weight, right? Because once we put the weight on the stick, the mass is not equally distributed like it was, roughly speaking, for the stick, right? The first number we got should have been around 50 centimeters, right? Pretty much everybody should have got a number around there because there was no weight on the stick and it was roughly equally distributed. But not exactly 50, right? So each of you guys has a different number. You put the weight on certain points, the center of mass of the system shifts according to where it is. And also according to depending on how heavy your weight was. And the groups received different weights, right? Some of y'all received 500 grams, some of y'all received 100 and I think it was 48. Then there was a 250 maybe gram weight that I weighed myself. Those were known quantities, right? And so we have these other constants that we either know or we had somehow measured beforehand, right? So I gave you guys the masses of the weights. This is the unknown quantity, but it is constant. The mass of the stick wasn't going to suddenly change on us unless perhaps if one of you guys split the meter stick in half or broke it into pieces, right? And then, of course, it's losing mass, right? But if you didn't do those things, the mass of the stick should have remained constant. And of course, the position of the stick, that's the roughly, 50 centimeter mark. Again, plus or minus some amount of centimeters for uncertainty. By the way, guys, in physics, we focus on uncertainty rather than sig figs. So I know you guys learned about sig figs in chemistry. Here we talk about uncertainty. So I should write this a little bit differently. I might say that the position of the stick is, maybe 50 centimeters. Well, I'll put the units at the end, actually. 50, maybe plus or minus 2 centimeters of uncertainty, right? Maybe even more. Maybe some of you guys had a position for the stick of maybe 47. That plus or minus 2 is just giving us a range around where we would most likely expect the true position to be, but of course the real world is messy, and so we have to incorporate uncertainty into everything. Anyway, one of the ideas that we sort of cobbled together, I sort of tried to point you all in the direction of was, okay, if I take this center of mass formula and I apply it to our situation, we get something kind of like this, right? And so you got to make sure you know what each of these quantities is referring to, right? But you notice the unknown quantity that we want is right there and right here. And then the rest of them are known, right? So this is known, that's known, that's known. The mass of the weight was given to you guys, that's known. And of course, this is known because we measured the position of the center of mass of the system, right? So everything else is known. So the idea is if we could algebraically solve for the mass of the stick, we could get some kind of formula that sort of spits it out to us. And so I just kind of want to briefly show you guys the algebra here. This is really not magic. This is just algebra. I would highly recommend doing problems this way as much as you can going forward. This is actually super useful. When you get into college and you take science or math classes, this is actually a much more powerful way to deal with data. Because if I have, 6 or 7 data points, one thing you might want to do is go ahead and just start plugging them in and then solve for mass of the stick here and here. But the problem is you're going to have to repeat that process for each pair of data points, doing the same exact algebraic moves over and over and over again. It is a lot more efficient and convenient to do the algebra first in these steps, then plug in your data down in the formula, and then just have the calculator or whatever you're using calculate the answer. And so you're going to be seeing that kind of style of problem in AP Physics later on too. There will be AP questions where there are no numbers involved, and the question might say something like, express the mass of the stick in terms of all other known quantities, or they might say in terms of the constant for the acceleration due to gravity, and so on, right? So basically all that means is you just want what you're looking for, an equal sign, and then everything else on the other side, right? However you need to do that mathematically, just doing some basic algebra. That's sort of a really common technique that you're going to see over and over again. So here's what I did after you guys kind of took your data points and were trying to figure out how to best incorporate them. I went ahead and found a 4th meter stick that you guys hadn't used or taken measurements from, and I redid the whole experiment myself, along the same lines that you guys did them. I tried to get 6 or 7 data points. Let me go over here. So once I had a free period, I went ahead and just tried to do the same exact thing, same exact kind of solving there for that mass of the stick formula. And this is the raw data I got in terms of a table. I have my independent variable, the position of the weight. Dependent is the center of mass of the system. And then I'm going to also keep track of what does this pair of data calculate for the mass of the stick in that 3rd column, right? I also have the first measurement of the quote-unquote position or center of mass of just the stick. So I had around 50.2, 50.3. 50.3. we could just sort of approximate and just, those are pretty darn close, so I might just choose 50.2. And so what I have here is a little Google Sheet, and I have, this is mass of the weight. This right here is position of the stick, position of the weight over there, center of mass of the system. Here's the calculated mass of the stick. So in case you don't know how to use Google Sheets, Excel, this is actually a super useful skill to have no matter what job you have in the future. Pretty much every job you're going to get, you're going to have to know how to use spreadsheets. So one thing you might want to do is first, let's sort of autofill a couple rows down with just the same number. You'll see why in a second. And we're going to use what's called a formula. So I'm going to type in this same formula that we sort of algebraically solved for in terms of keyboard characters over here. And I'm going to have it reference the cells with the numbers that I actually want. So I'm not actually going to type in 24.5 or 16. I'm going to click on them with my finger. I wish I had a mouse to show you guys, but I had to use my iPad because you'll see why later. So I'm going to type equals. The first variable in that formula is mass of the weight. So I'm going to click on that, which is the 295. You see how it highlights, and you see E3 show up after my equal sign. I'm going to do times, which you have to use the star button. That's what the keyboard equivalent for multiplication. Right? And then I'm going to put parentheses. Now I need position of the weight. So XW. I'm going to click on the corresponding data point for that. Now minus X center of mass. So center of mass of the system, that's the 24.5. Again, you notice how they're color coding the cells, and you can see them show up in the formula there. That's what you want. Now we're going to have divided by. That's going to be the slash. Another parentheses. Make sure you have the second set of parentheses. We're going to have X center of mass again. I'm going to click on that. So B3 again. And then minus XS, position of the stick. So I'm just going to say that's 50.2. Maybe we should have taken an average of some kind, but anyhow. Let me close the parentheses. Always close your parentheses. Click enter. And so this right here is my calculated value. That 90, oh, whoops. What is this doing? That 97.568 is my calculated value according to these two data points, right? Now here's the beauty of using sheets. Go ahead, slide this down, click autofill, and boom. It's going to automatically take that same template for the formula, but apply it for the new data points. So if I take a look at this formula, you can see it's using all the data from the same columns, but from that row, row 6, right? So it's just keeping the same template so that you don't have to type it in 600 times, right? So that's awesome. And so I'm sure a lot of you guys figured that out. And so now you have all these calculated values for the stick, the mass of the stick. But you might have run into some issues because, these seem pretty close together, and maybe in the middle of your data set, you might have some sort of bigger than normal number, or at least it just seems bigger than what it should be compared to some of the others. And that's kind of a subjective thing. In physics, we're not going to just throw out data because it seems wrong. Just use the data as it is. But I mean, if you were to ask me which, is there an outlier maybe, if I had to guess, it would probably be this number. And really the $1 million question is, why is that even happening in the first place? Because we solved the equation correctly, all the algebra is correct. We're using the data, I made as certain as possible. I was gathering this data as precisely as I could. And yet I'm getting this randomly maybe bigger than normal number. So what's actually going on here? Let me maybe circle back to the formula. and it's down here. So think about what kind of numbers, when I plug them in, might make this value sort of maybe explode in value, right? Think of like a worst case scenario. So in math, typically what ends up sort of throwing off a value is when you're dividing by really small numbers. So you might want to look at this denominator over here. The center of mass of the stick was around, we said like 50 plus or minus. It probably, maybe not plus or minus 2. Maybe we should say plus or minus 1 or something like that. I'm being very vague here. We'll be more specific later. But you notice what would happen if XS, the position of the stick, was really close. Oh, you know what? I said that backwards. We said that the position of the stick was around 50 plus or minus 1, 1 or 2 centimeters, right? So what would happen if we gather data about the center of mass of the system, and it also is, 50 plus or minus 1 centimeter, right? Or maybe to use hard numbers here, let's say the position of the stick, I said it was 50.2 for my stick. But let's say you end up with center mass of the system being 50.3 for one of the pairs of your data points. When you end up subtracting those, you literally get 0.1. That's essentially taking this top result up here and multiplying by a factor of 10, which is not a good thing, right? So if we, that very, very small, proximity, if you notice, where did my anomaly happen? I'm guessing this is the anomaly. It happened near 50 when I had a center of mass of the system pretty close to 50. Now, I had a big enough gap to where this number didn't blow up extremely big, but I'm sure many of you guys experienced an even bigger anomaly. I heard some people getting calculated values of like 300 grams or 400 grams, right? So actually, our method ended up causing us some issues, right? So you might just say, well, how about we just throw this out? But we don't want to do that, right? Because this is a totally subjective thing. What if that isn't really an anomaly? Like, who's to say that this is an anomaly and then this one is not, right? It's kind of a subjective gray area. So we want to look for something more solid and less affected by tiny errors. And for that, let me show you guys a little example here. I have this set of data that I just kind of put together. I wanted all the data points to be some kind of linear relationship. So this is basically the graph of y equals 2 times x, right? Really simple, with the exception of one data point. So instead of writing 20, I accidentally put 200. I purposely accidentally put 200. And so I took the average of the y column, and I get an average of 28, which we know, in reality, if we know that the relationship should be 2 times x, like we know that the average, if we go from like 2 to 30, and it's some very, very rigid, linear relationship, the average should be sort of in the midpoint between 2 and 30, maybe something like 15, 16, 17, somewhere around there. And this one outlier or anomaly is throwing off our average by quite a bit, right? I mean, if the average is around 16, I have just thrown off my average by 12 units, right? So what we want to do in physics is look for something that's not as affected by outliers. Namely, that's the trend line or the linear regression line or the least squares regression line, right? So what I did here is I created a chart, a scatter plot of the above data. You can see all the correct quote-unquote data points are clearly in a linear relationship, and then we have this high data point at 200. And we know what the slope of the line should be if we were to throw out the outlier. But again, granted, you already know it's an outlier. In the real world, we don't really know all the time where the outliers are. So we know the slope should be 2. And so obviously the outlier is affecting the least squares regression line a little bit, but not by as much as the average, right? So the difference between 2 and 3.29 is 1.29. That's definitely, at least, you're minimizing the effect of your errors a lot better than just taking the average of stuff. So I heard a lot of you guys, you had all these calculated values, and many of you were saying to me, hey, let's just take the average. Would that work? You don't want to do that. You want to do that as little as possible in physics. We want to use the least squares regression line. So how can we incorporate that into calculating the mass of the stick? This is a really strange technique, but it's actually pretty amazing. When I first saw this, it kind of blew my mind. So let's go back to, I'm going to change the color here. Let's go back to this formula. Let me rewrite it over here. All right, so we have center of mass of the system equals mass of the stick, XS, plus mass of the weight, position of the weight, over mass of the stick, plus mass of the weight. Okay. Let me rewrite this in a way that sort of highlights our independent and dependent variable a little bit clearer. Because we could write this a different way. So center of mass of the system is our dependent variable. That's kind of like our y. And the position of the weight is the thing that we actually chose, right? And mathematically, we could write the exact same thing, maybe more like this. So essentially what I'm doing is I'm dividing through each term on the numerator by the denominator. And I'm going to put xw out here. That's the same thing as putting it inside, but I'm just going to put it out there for visual purposes. Then we got plus mass of the stick, position of the stick, over ms plus mw. Okay, I want you guys to kind of look at this for a bit. Just really think about it. Think about this quantity here and this quantity here. In reality, the only thing that's truly changing is where we're putting the weight, right here, and then the resulting center of mass of the system. So what's happening with these two quantities? Is the mass of the weight changing? No. Is the mass of the stick changing? Well, we don't know what it is, but it's not changing. So this whole thing is constant. What about over here? So we know the mass of the stick doesn't change, mass of the stick doesn't change, mass of the weight doesn't change. Does the position of the stick change? No, right? The stick, unless again you break it to pieces or obliterate it or set it on fire, the position of the stick, it was that first number we found, that isn't changing. This is constant as well. So here's a thought. What if we were to make a scatter plot using this as kind of it's kind of like the x, right? And this sort of as the y, and we were to find the least squares regression between those two, what would the slope correspond to when we let the computer get our slope and our y-intercept for the least squares regression? This is your slope right here. This is your y-intercept. And we know that even if you have outliers, the least squares regression line is not as affected as the average, right? And what's great is this also gives us two different quantities or two different ways of calculating the mass of the stick. So, let's call this A and let's call this B. All right, so mathematically, what does this mean? That means that A equals mass of the weight over mass of the stick plus mass of the weight. I can solve this for mass of the stick, right? If I just do some simple algebra over here. Oh, whoops. Mass of the weight equals mass of the weight. I get this over here. Mass of the weight. A times mass of the stick equals, okay, I'm going to simplify this a bit. We're going to have 1 minus A times mass of the weight. Pause the video if you don't understand that step. Then I'm going to divide both sides by A, whatever A is, and I get this thing times mass of the weight. Okay, nice. So this right here is a formula of the mass of the stick in terms of the slope of our least squares regression line here and here, and then also the mass of the weight. And that's really, really useful to have because notice what doesn't show up. What doesn't show up is something like this, where we have some kind of subtraction on the bottom, where our errors can actually explode the value of our calculated value, right? That doesn't happen here. So that's awesome, because we know there's going to be errors, right? But we want to minimize their effect. We also have this secondary way to calculate the mass of the stick. We have B equals MS XS over MS plus MW. All right, I'm going to go on algebra autopilot here. So just slow down the video if none of these steps make sense, because I've been going on for a long time and you guys don't want to watch an 1.5-hour video. So I get it. All right, now let's group some MS's together. I'm going to subtract it from both sides. Factor out the MS and you get XS minus B times MS in parentheses. And then divide both sides by that quantity. So we have BMW, like the car, divided by that quantity should also be a formula for the calculated value of the mass of the stick. Nice. So we have two different ways to get a calculated value for the mass of our stick. So what I want you guys to do, try to use these better, more improved formulas to try to calculate the mass of your meter stick. I would do that in this video, but I get the sense that I've already gone over 40 minutes. I don't want to waste any more of y'all's time. So next up, look at the video that's sort of going to introduce the pivot lab that you guys are going to do.